Hello everyone. In this video, I want to show you how to properly assemble a worm with worm gear and then do a motion study on that. So I've seen a couple of videos online that they assemble it, but there are a bunch of important stuff that they're missing. The speed ratio, they are not doing a good job. They are just putting random numbers. There is clearly interference between the teeth. They put the input on the worm gear instead of just on the worm, so they don't know this is a one-way mechanism. So it's not just to put it together, you have to do it right. So I just want to talk a little bit about that. Okay. So as you saw, I put the motion on the worm. The worm is the input, the gear is the output all the time. That's the only way this mechanism works. The worm gear can never turn the worm. Only worm is the input, this one is the output, and the speed ratio is very, very low. In other words, the output only goes on for one tooth when the worm rotates one full rotation. So here I have 30 teeth, and this one is only a one-way thread. So the ratio here is 1 to 30. That's why we use worm and worm gear to reduce the speed ratio in a large amount instead of a multi-stage gearbox using spool gears. And the fact that only worm can rotate the worm gear, this is a lock mechanism for it. So if I have a load attached to the worm gear, like a crane or something, and this one is lifting up a weight, if the motor that is running the worm suddenly turns off because the worm gear cannot turn the worm, the mechanism would lock. So here we typically use it in hoisting mechanisms that want to lock in case the power is disconnected. And that's the nature of this mechanism, okay? The disadvantage of it is, of course, the friction. I have a big video about worms and worm gears on my channel under playlist machine design. If you want to know more about them, the design, the load and everything, force analysis, I recommend you do go there. But here we want to talk about SolidWorks. So you see here I used 5 constraints to place them properly, and then a gear mate to provide the gear ratio. And let me show you first the 1 to 30 in action here, although you have seen the video, but I want to show you more accurately. So here, if I now in here, I have no control over that. I mean, I can turn one of them, the other one would turn. But look here, I put it right on the right side, and look at the way that this handle that I added is placed. So now I'm gonna turn this one full rotation and see how much that one goes down. Okay, so we grab one of these edges or a point or something, and we go one full rotation like this, right? And now take a look here. You see that it went from horizontal, which was in the middle of here, to now in the middle of this point. So all it went down is one tooth. Okay, so the ratio is, as I said, since this has 30 teeth, it's 1 to 30. Okay, now how did I do it? I want to redo it for you here so you exactly know what I did with the 6 constraints. So here I'm gonna go ahead and start a new assembly again. And I'm gonna bring those 2 pieces. Okay, so here we go. I bring these 2 pieces, and there we go, right? So here are the parts, and now it is time to assemble them. First thing is make sure that this is a float. Both of them needs to move, so nothing should be fixed. The next thing you want to do is to make sure that, let's say this guy is sitting against a surface or something, right? That surface should be a fixed surface, so this guy cannot move along its axis. So let's say here I pick the right plane of the assembly, and then I can pick either the front, the back, or the mid surface of this and make sure it sits against there. So here, this one has a mid plane, and let's see if I can find it. Actually, that's the wrong part. It's this one. So it has a mid plane, and I force these two to be coincident. There we go. You see, so now this one cannot move in this direction. All it can do is to move along the X and Y direction. Look here, it cannot go. Now to fix it in the X and Y direction, one thing you can do easily is to make sure that this surface here and the origin are concentric. So you pick that surface and you pick the origin and you force them to be concentric. Okay, like this. This way, this gear is going to be fully fixed. The only thing it can do is a spin. So this gear is now placed properly. Now we need to go about the worm. For the worm, what we need to do is first make sure it's right above the gear. So you see right now, this one should be, the axis of it should be parallel to the bottom floor, right? Or you can make it, the axis of it, coincident with the right plane of the assembly. So I pick this, I make the axis visible, and now I pick the axis of the object and I force it to be coincident with the right plane of the assembly. So this will orient the worm gear properly. So you see now it's right above it. Okay. Now that you got this, it is time to place it at proper distance. So there are several degrees of freedom you need to take away. One of them is this. You have to fix that. The other one is this. You need to take care of these two distances and then you apply the rest of it. So what we need to do here is to put them at proper distance. One thing that I saw in that video, I don't want to say by who, but the thing I saw is the person just brings it down visually and just put it in some good place that, okay, now this looks good to me, and then goes ahead and then here he or she picks this distance from here, let's say, to the top plane and applies a distance here. Okay, so go, okay, that when it was 179, this distance here, when it was that number, whatever number it was good, so let's pick it as that. Okay, so that is not the proper way to do it. The other important thing is, even if you want to do it, you have to go and click on interference detection and make sure there is no interference. You see right now there is no interference. But does it mean that it's good? Well, in order for the teeth to be properly engaged, this distance, I mean, if you put it way high up, of course, right, there is no interference right now, but they are too far away from each other. So the proper distance is going to be the diameter of pitch circle of this plus the diameter of pitch circle of this divided by 2. Now, what are these here? Fortunately, these two files that I got, and I got them from the GrabCAD, so they are not my files, okay? I am not claiming anything about these components. And here, if you go down to equation, the numbers are here. So if you look, pitch diameter of this is 241, 195, 197, right? And if you look at the other component, you can see under the equation of this one that, let me show you, that the diameter here is 80. That's this guy here, I checked it. That's this diameter D1. So you need to add 80 to this number here, and then divided by 2, that's the proper distance, right? So let's go ahead and do that. So here we go, and we say I want a mate. And for that mate, I want it to be the distance between that axis and the top plane of the assembly. And then I go ahead and provide the distance here. So this is going to be equal to 241, 197 plus 80 divided by 2, and then it is in millimeters. Okay, so it's going to be these many inches. There we go. And if you want, you can change this to mils because everything here is mils. So now this is the proper center to center distance, or axis to axis, because axes are askew here. Okay, now this is the proper distance. Now once you have this set, so this degree of freedom is set now, now you have to fix the other one. Okay, so now you can move in this direction. So now you have to bring this in a place that it has 0 or minimal interference. Ideally, it should be 0. One thing I found though is when I put it at that distance I just showed you, when I put the axis to axis distance at that number, it always have some very, very small interference on the teeth. And let me show you that here. So as I said, first, let's say visually, I put it somewhere here that has bare minimum, let's say interference like this, but you see here you have some, right? So try to make it minimal, like that. And now you can go ahead and measure the distance if you want, right? So let's say from the front plane of the assembly, if you want, to this guy, you can measure the distance. So I go to evaluate, measure, and measure the distance from this plane to here. So let's see if I can do that, or at least to origin, if I can get that distance. And the distance you want in this case is the Z direction, correct? So what you need is the distance in the Z direction. So let me get that. And you see it's 225.08. Okay, so now this is what I'm gonna do. I pick this surface and I pick the front, and we are going to use that number. Okay, so let's go ahead and do that. So we put them at the distance again, and 225.08. That should be the distance. And hopefully if I put it at this distance, now I don't have interference, but you have to confirm that. Just putting a number doesn't do it. So here, if I go to evaluate and say interference detection and calculate, you see there is some small patch of thing here, and there are a few other ones here and here. And you might say, well, that's right, it's this distance, but look, they are all on the same side of the teeth. If you look, they are all on the left side. So if you move the whole basically worm a little bit to the right side, you are going to get rid of them, right? So we can say, fine, this is the distance between these two. If I make this distance a little bit smaller, because this face is fixed, this one moves a little bit to the left. So I go here and try to reduce it gently, right? So let's say I get rid of this 0.8 and take a look at it again. And again, you have to redo the same thing. Now look, still on the left side, and you have those. So that was not clearly enough, and you can keep doing that. And I did this several times, and I found that regardless of how much I try here, I will always get something. And the reason for that is the profile of this worm is too thick. So one thing I did was I went into the CAD file of the worm and reduced the width of the profile to something more appropriate. So you can do that and make this a little bit thinner, or reduce the thickness of this profile here. Another thing you can do is gently, very gently lift this guy up, okay? But remember, you should not really lift it up much. You see, right now it's bare minimum on the left, and there is nothing on those other sides. So you need to make sure that this is the appropriate distance here. So what I did here, I lift this up by less than a mil, about 0.7, 0.8 mil, gently lift it up. And now look, when I do interference, there is no interference. Again, this is not the best way to do it. Ideally, the profile should be appropriate size, that when you do some trial and error on this distance, one time all of the patches of interference are on the left side, the other time they fall on the right side as you change it. So you can do some interpolation between those two and find the perfect distance that will give you no interference. But again, in this case, I did a lot of trial and error on these, even when I reduced the size of it a little bit, and didn't work. So I could use more size reduction, or I could lift this up gently. So I prefer to do a little bit lift and a little bit profile trimming, and now there is nothing. Okay, it is perfect. Now it is time to apply the gear constraint. So now we go to assembly and we say mate mechanical, and then we pick the gear, and the surfaces we pick could be, let's say, this one and this one. But pay attention that here it is using the size of those as the reference for speed ratio. This is absolutely not the speed ratio. Be very careful about that. When you pick a feature, it is going to use that. That is not the gear ratio here. Here, the gear ratio of the worm, which is the first number, should be like 1 mil, and this one should be the number of teeth, 32 mil. Again, there should not be mil, but here it apparently wants some dimensions. So I'm manually forcing 1 to 32, or 30 actually. It's 30, not 32. 1 to 30, which is exactly the number of threads here. 1 over what? Over the number of teeth here. This is going to give you the proper speed ratio. Now pay attention, if you have seen, it says the number of teeth on this one over the number of teeth on that. That's not right. So you cannot count these and say, hey, I have like 10, 12 threads, 10, 12 ups and downs, right? 12 parts of the thread, and divide that 12 by 30. No. Or you might say, well, here I have 3 or 4 teeth engaged. I divide that 3 or 4 by 30. No. The number that you use for the worm is actually the thread. How many threads, how many ways of threads or starts you have here. If it's a one thread, a single thread, one single helix, that's 1. If you have a double helix on it, that's 2. If you have a triple, that's 3. Okay, so in this case, it's just 1 over 30. Now, let's see if I move it now, would I receive the nice behavior or not? And you see that I'm getting beautiful behavior. And now if I go back and check on the interference again, ideally I should not get one. There we go. You see? So although I moved it, it is not giving me any further interference. Pay attention, I gave the input only to the worm and I use the proper input ratio. And now if I go to the motion study and if I apply a motor to the worm, that's the only place you can apply it, right? So here I can go ahead and apply a motor to this guy and make it a little bit, even 100 is good, okay? And let's say run this for 20 seconds or something, and then do a motion calculation analysis and run. Look, you see how fast this one is spinning? This one is spinning 100 RPM. That's very fast. This one is going very slow. Okay, yes, so let's look at it again from this side. You can see better. Look how fast this one is spinning and how slow this one is spinning. This is proper motion analysis on a worm gear. So hopefully you learned something and you found it useful if you want to perform a worm gear proper assembly and proper analysis in SolidWorks. Thank you. I'll see you in the next video.